if we have a function whose domain now is in R3. So these are the kind of functions that we cannot actually graph, right? Remember that if the domain is in R3, we need one more dimension for the z, for the last axis, so we will need 4 dimensions to represent this one. Though we can always represent the domain because the domain is in R3. So we can actually define also a triple Riemann sum just by generalizing the double Riemann sum that we saw for 2 variables. So in this case, instead of being a rectangle, now the basic unit is going to be a rectangular prism or a box where we have 3 variables now, x, y, and z, where each of the variables is going to vary between 2 constants. So a prism P is going to look like something like this, where the x vary between A and B, the y vary between C and D, and the z vary between P and Q. So at the end, this will be how it looks like the domain of this function. And we can generalize the idea that we use for rectangles to a rectangular prism like this. And so we are going to do a subdivision first for the x interval, a subdivision for the y interval, and now a subdivision for the z interval too. And then the 3 together, they are going to determine a partition of the whole prism. And we're going to have that the differential of the volume is going to be just the multiplication of these 3. And so, as before, we can choose a point in each of the small prisms, and we can define the triple Riemann sum as the addition of the function evaluated at those points where the variables travel through the whole partition. And then when we consider a partition big enough, let's say when m, n, and l goes to infinity, then this is going to be the definition of triple integral of the function. So when we get a subdivision where the prisms, the little prisms, are small enough, and so then in the limit, the result of this sum is going to be the triple integral. And the way to calculate this is going to be given by Fubini's theorem, by the version of Fubini's theorem for 3 components. That what it says is that the triple integral is the same that calculating, there should be f, x, y, and z, where the variables are x, y, and z. So we can integrate first respect to x, and then respect to y, and then at the end, only at the end, we do the z. But what Fubini says is that this integral is the same that varying this sequence in any other order. So we can do that dy dx dz, or dz dx dy. So all the possible permutations of the variables will give the same triple integral. So for example, let's calculate a triple integral of this function, in this case, of 3 variables, where the prism is given by this. The x vary between 0 and 1, the y 0 and 2, and the z 0 and 5. And so the triple integral over this region of this function dv is going to be equal to, and so we do the integral in any order according to Fubini's. So for instance, I'm going to do outside the variation of z. That will be the last one I do. And so here I'm going to put the variation of y that vary between 0 and 2 dy. And then finally inside I'm going to put the variation of x between 0 and 1 of the function, that in this case is this one given here, x plus 3z dx. And so, as before, we start by doing this integral where we consider that the only variable here is going to be x. And when we finish this integral, then we're going to do the other one. And finally, the last one will be respect to z. Okay, so let's start. So we leave outside these two, right? So these two, we are not doing anything about them. So we are going to solve first only this integral. So let's integrate this with respect to x. So the integral is going to be x squared over 2 plus, and this is a constant respect to x. So it's going to be 3z x. And this we need to evaluate between 0 and 1. Okay, so this is the integrand here. So let's solve this and let's keep these two integrals for the end, dy dz, and let's evaluate this at 1 and at 0. So this one evaluated at 1 is going to be 1/2 plus 3z, right? 3z multiplied by 1 minus 0, so it's going to be just this. Okay, so now the next integral is going to be then this integral respect to y. So I leave outside 0 phi dz, and I'm going to integrate this respect to y. So here there is no y, so it's just a constant, so it's 1/2 plus 3z y. And this function is going to be evaluated between 0 and 2. So this is then the integral 0 and 5. And let's evaluate then the function between 0 and 2. So that will be just putting a 2 here, right? So it will be 2 times 1/2, which is just 1, plus, and then 2 times 3z, that is going to be just 6z. And so this is then the last integral that we need to solve. So this integral respect to z, we integrate. The integral of this is going to be z plus 6z squared over 2. And then we need to evaluate this between 0 and 5. So let's plug in. So here we have first 6 over 2, this is 3. And so let's substitute z by 5. And so we are going to have 5 plus 3 times 25. And so the final answer of this is going to be 80 units. So the triple integral of this function over this region is equal to 80 units. So let's calculate now a triple integral of a function in a general region. I mean, we can extend the Fubini theorem from variation between constants, just as we did for double integrals. The outside integral should be between constants, but the ones before can vary between functions. So in this case, so let's start. We can see that the variable z is going to vary. We have here the three components. The z is going to vary from 0, since I start here, to, and in here is going to be determined the upper bound by the actual plane. So then we can say right away that z is going to vary between 0, and we solve for z here, and we are going to get here 6 minus 2x minus 3y. So then we have the variation of z between two functions, where this function depends on the two other variables, x and y. So that means that z is going to be our most inner variable. And then we keep going towards outside. So the y is also going to start the variation from 0, and is going to finish from, is we study here, this is x, this is y, the variation of y. Y is going to vary from here, and is going to go all the way until where this plane intersects actually the xy plane. So let's calculate this intersection. This is just when the z is equal to 0. So if we put here z is equal to 0, we have that 2x plus 3y is equal to 6. And so we can see here that 3y is 6 minus 2x, and then y is equal 6 minus 2x over 3. And so this is going to be the upper bound for y. And observe that y is still dependent, but now on just one variable, the other one. 6 over 3 is 2 minus 2/3 x. So this is going to be then the upper bound of the variation of y. And finally, the variation of x in the same way is going to start at 0 and is going to end here with the intersection that now where y and z are equal 0. So we put those things here and we get that 2x is equal to 6. And so x is equal 6 over 2, which is 3. So this is going to be the upper bound of the variation of x. So we see that now x vary between two numbers, and so this is going to be the outer integral. So this triple integral then over this region of the function f dv is going to be equal to the integral from 0 to 3 dx, right? So this is going to be the outer one. And then the integral from 0 to this function that depends only on x, dy. Y is the one that is varying in this range. And the most inner one will be the variation of z that is between 0 and this function that depends on x and y, 6 minus 2x minus 3y. And this is going to be the variation of z. And here we are going to put the function f, that is the function f of x, y, z equal x. So be sure that you check here that before was the incorrect function. So this is the function that we are integrated in this example. So we're going to write here just x here. And then we are going to calculate these integrals one by one as we did before. So first we're going to calculate this integral respect to z. So let's start. The primitive of x is xz, right? So since x respect to z is a constant. And so we evaluate this between 0 and 6 minus 2x minus 3y. So the evaluation of that is going to be x times, and so instead of z, we're going to put 6 minus 2x minus 3y. Then the integral 0, 3, I'm going to copy everything the same. This is 0 and 3 dx, and inside we're going to put this one, 0 to minus 2/3 x. And so inside is where we calculate now what integral goes. So it's going to go this one, that is actually 6x minus 2x squared minus 3xy. And this is going to be dy. So this is going to be then our next integral. So we are going to calculate the primitive of this respect to y, right? So considering now that the variable is y. So the primitive of this respect to y is going to be then 6xy minus 2x squared y minus 3xy squared over 2. And we need to evaluate this between 0 and 2 minus 2/3 x. Evaluating now this function at here, so we're going to get here 6x times all that, right? 2 minus 2/3 x minus 2x squared, 2 minus 2/3 x minus 3x, 2 minus 2/3 x squared over 2. And so doing the operations here and simplify, we have to multiply everything here, so we get that this is 12x minus 4x squared minus 4x squared plus 4x cubed over 3 minus, we need to do this square here, that will be 4 minus 2 times 2 times 2 over 3x, and then plus 4 over 9x squared. And so doing all this operation over 2, we get here minus 6x plus 4x squared minus 2/3 x cubed. Let's combine like terms, and we get here, we have all the, putting all the x together, we get here that this is 6x minus 4x squared plus 2/3 x cubed. So we did then the evaluations, and it's just that thing here. So now putting everything in the integral that we were calculating, we have that this is actually equals to, and so we get here integral between 0 and 3, and so all this one here is this result that we got here. So will be just 6x minus 4x squared plus 2/3 x cubed dx, right? So this is the last integral we need to calculate here. Okay, so let's do the primitive of this. That will be 6x squared over 2 minus 4x cubed over 3 plus 2/3 x4 over 4, right? And this evaluate between 0 and 3. So let's simplify here. 2 and 4, we get just a 2 here. 6 and 2, we get a 3 there. And so this is just 3x squared minus 4x cubed plus x4 divided by 6, evaluated between 0 and 3. So we substitute there 3, we have here 3 squared times 3, this is 27, minus 3 cubed times 4, this is 36, and then plus 3 to the 4th power, this is 81 over 6. And so we get that this is 27 minus 36 is minus 9, plus simplifying here, this is 27 half, and this is 9 times 2 is 18. 27 minus 18 is 9 over 2. So then this is the result, 9/2 of the whole integral that we set up to calculate. In the same way that before, we had that the average value in a volume is going to be the same that in the double integral, only that now we're going to divide by the volume of the region. So it's going to be given by the triple integral on the region divided by the volume of the region. That will give the average value of the whole function on the solid R. And as before also, we have that if the function that we are integrating is a constant function equals 1, so it happens that the triple integrals goes down one dimension and we recover actually the volume of the region. So we can also, even though double integrals are to calculate volumes, we can also do a triple integral to calculate the volume by just integrating the function equals to 1.